We are going to use Stokes' theorem to convert this curl integral into a line integral. So remember that Stokes' theorem says that the integral along a curve of f dot dr is equal to the surface integral of curl of f dot ds. Now, when you go to apply Stokes' theorem, there's always a question of which one of these two integrals you're going to end up evaluating. You end up evaluating the one that simplifies the process, and in this case, we're going to be converting the right-hand integral into the left-hand integral to end up evaluating a line integral. In order to do this, we need to parameterize the boundary. Because after all, the boundary curve C that bounds S is the thing that we're going to be integrating around. So let's draw a set of axes and figure out what this surface looks like. We've got our standard X, Y, and Z axes. And I'm going to draw this cone, y squared equals x squared plus z squared. Think about the fact that for fixed values of y, this is a circle, x squared plus z squared equals some radius squared. So this means that this will have its axis of symmetry as being the y-axis. And the cone will spread out like this. It'll be bounded by y equals 0 and y equals 3. This right here is obviously y equals 0. Now I want to zoom in a little bit on this and talk about what the orientation would be. Think about the fact that this is oriented in the direction of the positive y-axis. So in the direction of the positive y-axis means that if I'm standing at this point right here, the normal that I'm interested in, the unit normal, is going to point in that direction. This is as opposed to pointing in the other direction. There are always two options. So the surface integral that we'll be considering is oriented this way with this highlighted thing right here. Now think about this. The surface is oriented so that walking around C, that's the boundary curve, walking around C with your head in the direction of N, puts the surface on your, can you complete the sentence? Puts the surface on your left. This orientation of C is the one that is positive. And allows Stokes. So think about the orientation induced by this unit normal vector. If you're right there, then the interior of the surface is on your left. As you walk this way along the curve, you keep the surface on your left. And by the surface, I mean the interior of the cone over here. So that means that the orientation of this thing, we'll zoom back out, the orientation of it is going to be this way. This is the positive orientation on the curve that is induced by the orientation on the cone itself, on the entire surface. So there's one more thing that we need to do before we parameterize the boundary. It's that we need to draw it in the XZ plane. specifically in the plane y equals 3, and then we'll allow x and z to vary however they do. Now, I want you to think about this. In order for the x and z axes to form the familiar capital L shape, where you've got the z pointing up and the x pointing to the right, you need to look at it from this perspective. You need to look at this from the negative y-axis. If you think about how this rotates in your mind, if you want x to be to the right and z to be up, you do need to look at it from the negative y-axis. And from the negative y-axis, this orientation that we just described, is going to be like this. Now, think about looking at the left-hand portion of this circle. At the left, you're looking at right there. On the left, this is going up. So that means it will be oriented this way when viewed from this perspective. Now, this seems like it shouldn't be true because after all, this made it seem like it was counterclockwise and this looks like it's clockwise. But keep in mind, this is due to a change in perspective and you have to be able to think in 3 dimensions here. So using this parameterization, or using this perspective rather, we can draw a parameterization for this, x, y, and z. This is a circle. What is its radius? The radius is 3 because this is x squared plus z squared equals 3 squared. That means it is a radius of 3. So x will be equal to 3 cosine t. Y will be equal to 3 sine t, except it's going in the opposite direction. And so z needs to be equal to negative 3 sine t. Cool? Cool. Y is the easy part because y is always 3 along this curve. It's in the plane y equals 3. So if r is that, r is 3 cosine t, then 3 and negative 3 sine t, we can use this to form dr. This will be negative 3 sine t, then 0, and then negative 3 cosine t. Okay? This is one of the ingredients that we need. We now need to get f. So f of r, well, we're given that f is this, x squared y cubed z plus sine of xyz plus xyz itself. So x squared y cubed z and sine of xyz and then xyz alone. We need to rewrite these in terms of the variable of parameterization, in terms of the t. So let's put in the r values. X squared times y cubed times z, that's 3 squared times 3 cubed times 3. That's 3 to the 6th power, which is 3, 9, 27, 81, 243, 729. There's a minus sign, so it's negative 729. X was squared and z was to the 1st power. So that's sine t cosine squared t. Now sine of xyz is the j component. That's sine of 3 times 3 times 3 is 27. There's a minus sign. And let's see, sine t cosine t. Okay, and because we just did xyz for the inside of that, we can copy that as the k component. So now f dot dr is going to be, we're going to use this and this and form the dot product of those. So f dot dr is going to be negative 729 times negative 3 is 2,187. Sine squared t cosine squared t. Oops, I always begin doing that. This is not a vector, it's a scalar. And this is plus, what's the next part? It's 0, because 0 times sine of whatever, that's going to be 0. So 0 which is always nice to hear, especially because this was going to be so nasty. And then let's see. The last part is these two times each other. So that's plus 81 times sine t cosine squared t. Whenever we evaluate an integral, we always need the bounds of integration. So I didn't even mention this at first because I figured that we've done this enough, but think about the range of values for t that will cause this circle to get traversed exactly one time. It's going to be from 0 to 2 pi. Whenever we parameterize a circle, we very reliably use this bound for t. So this integral has two parts. There's going to be the first part and the second part. Let's do them separately. For the first part, it's going to be 2,187 times integral of sine squared t cosine squared t dt as t goes from 0 up to 2 pi. I'm going to rewrite the integrand, and here's how I'm going to do it. We know that 2 sine t cosine t equals sine of 2t, right? This is an identity. You know this from pre-calc. So I'm going to work with this a little bit to get the left-hand side to be what our integrand is. I'm going to divide by 2. That turns this into 1/2. And then I'm going to square everything. So this becomes sine squared cosine squared. And on the right-hand side, this is squared as well. This is now 1/4 sine squared of 2t. And this hasn't made it integrable yet because we don't have an integral for sine squared, but we do have a conversion. Remember that sine squared turns into 1 minus sine of 2 of the argument divided by 2. Now be careful here. There's a little bit of a twist because this is 1/4. That's from before. And then times sine squared of t. No. This is sine squared of 2t. So the 2t is going to get doubled. It's going to be 1 minus cosine of not 2t, but 2 times 2t. That's 4t. And this whole thing over 2. So just to emphasize, this right here, this is sine squared of 2t. Do you see how that fits together? I bet you do, because you're smart. Okay, then this can expand to become 1/8 minus cosine of 4t over 8. This can be integrated. So now we're going to say that this original integral becomes 2,187, don't forget that part, times the integral from 0 to 2 pi of 1/8 minus cosine of 4t over 8 with respect to t. At this point, you may be like, oh, great, well, it's not too hard, but I have to do this integral. You don't really have to do this integral, though, because look, cosine of 4t. Now, I want you to think about this. When you integrate a trig function over an entire period, that causes the integral to be 0. And if you integrate over 2 periods or 3 periods or 4 periods, guess what? The same thing happens. The integral ends up being 0. The period of this function right here is not 2 pi. It's been cut down by a factor of 4 to get pi over 2. Well, think about this, 0 to 2 pi. That is 4 of those periods. So guess what? This right here, this is going to contribute a grand total of 0 to the value of this integral. Cool. So the only thing you have to do is do the 1/8 times 2 pi times the length of the interval. So this will be 2,187 times 2 pi over 8. That's pi over 4. So this will become 2,187 pi over 4. Now remember, this is only the value of the first integral. We still need to go and get the second one. So we'll box that. And then I'm going to say numero dos. What is that going to end up being? That's 81 sine t cosine squared t. 81 integral from 0 to 2 pi of sine t cosine squared t dt. Whereas the first integral was not susceptible to substitution, this one is, because now you've got the squared and first power pattern. That means we should choose u equal to cosine t, making du equal to negative sine t dt. We're also going to change the bounds of integration to u of 0, which is 1, and u of 2 pi, which is cosine of 2 pi, is also 1. At this point, you may be licking your chops, and good for you, because if you take an integral from 1 to 1, that's going to be 0. Let's just make sure that it works by making sure that the integrand can be completely converted. So this will be 81 times integral from 1 to 1 of u squared times, and du is negative sine t dt. This is sine t dt. So not much is missing there. It's just a minus sign. Negative 81 integral from 1 to 1 of u squared du. There is no need for you to calculate this integral because it's integrated over a single point set. And the definition of such an integral is that it's equal to 0. So the final integral, the whole thing, is 2187 pi over 4. And if you think that's bad, well, maybe try and evaluate the curl integral, which would have been an absolute nightmare, because look at how bad these functions are. You're going to need to take the curl of that and then form the dot product with the ds. That means like ru cross rv. It would be an absolute catastrophe. So although this isn't easy, it still does showcase the power of Stokes' theorem in being able to find answers that would be very, very difficult to find any other way.